Okay. Yeah, Ali, and all the organizers for having me here. It's a great honor, and it's not like, okay, the first conference organized by Ali, and all of them are absolutely excellent in every respect. So thanks again. And, well, let's start. Okay, this is, okay, Chicago boardroom, our connection. You can immediately recognize. And those are collaborations. And I'm going to touch actually a little bit more than it was planned in the beginning, not only ferroelectrics, but also a little bit of superconductivity. So we have the full list of our collaborators. And let's get started. Oh, okay. Not the right direction. Okay, first the dedication. Okay, I cannot, okay, my French is more than rusty, so I wouldn't risk to pronounce this quotation from, okay, Marcel Proust in French. And it says the tail wedge of discovery consists not in seeking new landscapes, but in having new eyes. And this is, okay, you just, because I can't control it, and I don't know how well I'm heard. Okay, so the last century, it was actually the time of what is called topological revolution. And basically it was this fundamental work by these three people, Vadim Berezinsky, David Taulis, and Michael Kosterlitz. Two of them got Nobel Prize for their discovery. Oh, thanks. And unfortunately, Vadim Berezinsky didn't live long enough to get it. And this was indeed the revolution, because before, well, it was another great discovery, basically, okay, Landau's discovery of one, which is considered one of the most fundamental in condensed matter physics, the possibility of the spontaneous symmetry breaking and phase transitions, this theory of second order phase transition, which is just the symmetry breaking. And then, but since then it was believed that actually every state of matter should have what is called order parameter, and other states of matter just do not exist. And one of the achievements of this Berezinsky-Kosterlitz-Taulis new kind of phase transition was the finding that there are actually states of matter which are not characterized by any order parameter, but are characterized by topological order. And what we're going to do, actually, we're going to combine these two things today in what we're going to talk about. And this is basically the contribution, okay, so this is symmetry and topology, and there is a contribution of two great minds again of 20th century, Amy Noether, who actually put the foundation of all the contemporary physics. Actually, we start our study of physics from what she created, because her achievement, which is called Noether theorem, is that if the system has some symmetry, then there is some conservation law corresponding to this symmetry. And Vladimir Arnold formulated one of the deepest theorems in the topology of the 20th century, and this is exactly Arnold's theorem. Okay, sometimes they refer to this as Kolmogorov-Arnold-Moser theorem, which we're going to explore during our presentation all the time. Well, those are just beautiful examples of what we call symmetry. We know this pretty well, and this can be considered as topology. We can see vortices in one of the great paintings, and vortices is just the topological excitation. Okay, now, what is Arnold's theorem? okay, we'll just talk about this a little bit later, but the statement is extremely simple. Suppose that we have incompressible liquid, for example, and this incompressible liquid is like sort of confined in a finite volume. And then Arnold have shown that only two configurations for this liquid flow is possible. One of them is very familiar to everybody who is doing superconductivity or hydrodynamics, which are just vortices. But there is another, a little bit more exotic configuration of this liquid, which is sort of like self-linked, and which is called Hopf vibration, or okay, simply Hopf. Why this is interesting? Why it's not just the like mathematical construction? Well, there is another thing which we all know, but we all miss in a beautiful Feynman textbook on statistical mechanics. There is a small chapter, and when we are students, we are really lazy to read it, which is called Another View, or Another View on Superconductivity, and where Feynman formulated that basically superconductivity can be very well described by hydrodynamics of the superconducting condensate, and that this liquid is basically this incompressible liquid, and then it means that this Arnold's theorem applies to every superconductor. And what does it mean? Well, immediately, if we introduce the gauge field theory to describe these topological things, it immediately means that our Hopf is nothing but very well-known Bohm-Kasher interactions between electrons and, let's say, vortices for the moment. And why this interaction is so important? Because this is a really long-range interaction. So I remind, what is this about? Okay, we know pretty well what is Aharonov-Bohm effect, meaning that if we take, for example, electron around some magnetic flux, then the phase of the wave function acquires some phase, and then, and this doesn't depend on the distance. This doesn't depend on how large is the radius of this circle. And then one can construct a gauge theory for superconductors, and we'll talk about it in a minute. A new kind of superconductivity can appear. Well, first of all, this kind of constructions describes all the existing superconductivity very well, and the phenomena which were not possible to describe before. For example, with this gauge theory, it is possible to construct a theory of the superconductor insulated transition. Beautiful experimental fact. Until recently, no theory did exist. And another thing, which we are going, also to talk a little bit more, that these topological excitations, Hopf, actually appear in ferroelectric nanoparticles and give rise to some beautiful properties of them. So let's start a few words about superconductivity. So to construct the theory, what we have to do is to just, to draw actually the world lines for vortices or for magnetic charges and for the usual charges. And then we can immediately write down these Aharonov-Bohm-Kasher interactions and write this, what is called, the action, Aharonov-Bohm-Kasher action, which immediately takes into account all these topological excitations. And as a next step, this action is called Chern-Simons action, and it quantifies, okay, the field theory for this like infinite range Aronov-Bohm-Kasher interaction. And as a next step, we can use symmetry consideration against, this is a textbook exercise, we can write down into the action all the terms which are required by the symmetry, and what we can compose the action, and we can introduce gauge fields which make our all interactions local as they should be, because we don't want them to go instantaneously on the infinite distance. So we have the usual kinetic terms in our action, then we have our Chern-Simons topological terms there, and this action immediately describes, for example, superconductor insulated transition. Actually, it can describe the GIF sort of like phenomenological theory on the Ginzburg-Landau level of high temperature superconductivity, and explain why these high temperature superconductors do exist and have this high temperature. This we were discussing some other time, and now move on. And what I would like to say is that as soon as we construct the theory of the superconductor insulated transition, we immediately see that there are three phases which do exist in the vicinity of this transition. One of them, of course, is superconductor. Another is a new phase, and it will be it will be Carla Trugenberger, who will be giving a talk, which I invite you to attend, where a theory of superinsulator and related phenomena will be constructed. And then, if we analyze a little bit, what happens because of this long-range Aronov-Bohm-Kasher interactions, we will see that if we have special superconductor, which has in a normal state large dielectric permittivity, we will see that we get superconductivity of completely new kind. The usual superconductivity is described, as you know very well, very successfully by Ginzburg-Landau equation, which is by definition local equation, and in which, all the superconductivity effects, Meissner effect, which is like the basic property of superconductivity, in terms of field theory is called Anderson-Higgs mechanism, and it means that our electromagnetic field acquires, or gauge fields acquire a mass. If we analyze what happens in a superconductor, which stems from a metal which is in a normal size, normal state, has a high dielectric permittivity, we'll find out immediately that this Ginzburg-Landau approach doesn't work. Ginzburg-Landau functional becomes non-local because of this long-range interactions. It doesn't apply. We cannot describe the superconductivity with Ginzburg-Landau equation. I repeat it again. And this is new kind of superconductivity which appears, which we called, well, we couldn't invent a better name, but type 3 superconductivity. Christina, who is here, will be giving a talk on it. And this is new kind of superconductivity, completely new. For example, in this kind of superconductors, usual abrikosov vortices do not exist. Just one of the features of these new superconductors. So I invite you to attend Christina's talk. And we now move on from superconductivity to ferroelectrics. But before that, I have to mention that this kind of new superconductors, they have inherently granular structure. And this granular structure occurs because the system remembers that it has superconductor insulated transition, and then in the vicinity of this transition, every superconductor has a granular structure. It's like superconducting droplets, which are connected by the tunneling Josephson junction. So again, Christina is going to talk about it in a much more detail. please come. Now, okay. Topological materials is quite, let's say, fancy name. A lot of things which we call topological materials, and one can immediately ask if ferroelectrics do belong to the same class of topological materials, and if so, what is so topological about them? Well, we know pretty well what is ferroelectric. It's just like, okay, to entertain you, because you know this better than me, it's the same as ferromagnet. It's just the material which has spontaneous electric moment, and it's characterized by spontaneous polarization there because of its construction. And yes, there are a lot of publications in which topological excitations in ferroelectrics have been seen. They carry different names. Well, vortices, of course, they have been seen. There are skyrmions, beautiful topological configuration. But basically, it can be, well, we're not going to talk about this today, but basically all these configurations are reduced to two of them, according to Arnold's theorem, Hopfians and vortices. All the rest are one or another modification of this basic two. And, well, why they are so interesting? Because they split into the domains, and these domains, well, they follow exactly this Landau-Lifshitz-Kittel domains theory, and okay, these domains describe their beautiful properties, and this can be described by usual Ginzburg-Landau functional, which is in connection with ferroelectrics, it's called Ginzburg-Landau-Devonshire functional. So everything is quite obvious. One thing can be immediately noticed, that if we have ferroelectric nanoparticle, and then polarization is trying to be tangent to the surface confining this nanoparticle, because then there are no charges and this minimizes the energy. And then there is immediate analogy between the hydrodynamics of incompressible liquid and the physics of ferroelectricity in ferroelectrics. And then it means that this Arnold's theorem, now, okay, don't bother reading it, it's just whatever, it's just this, this famous theorem from this famous book, this is Vladimir Arnold, saying that in this mathematical language that there are only two topological excitations that can exist in the confined volume, and then that because of this self-linking, it should be finite knotting or helicity in this Hopfian formation. And this is basically the illustration of this notion once again. So if we start introducing or polarize our ferroelectric nanoparticles, only two topological excitations are possible, vortices, Hopfian, and of course this nanoparticle can split into the cells. Each of them is carrying each of these topological excitations. Well, this is just the illustration we have. Yes, okay, these illustrations, well, it's not a real experiment, unfortunately yet, or not made to this extent, but those are numerical simulations. Numerical simulations of a ferroelectric nanoparticle in which we can have, if we use the parameters of one of the most, let's say, technologically used one, and we found that it forms different topological configurations. So this is just, okay, a vortex made by the polarization lines. Then if we increase, actually, applied electric field, we can really form a Hopfian within this nanoparticle. Okay, this is just the illustration of this Hopfian, which has, okay, at the pole, it has like the vortex, exactly in okay, according to this Arnold's theorem. So here is the place for the Hopf-ion, and this is the cell or part of this nanoparticle which carries vortices, and Hopf-ion has non-zero chirality. This is another illustration of this Hopf-ion-like structure in a nanoparticle, just numerical simulations. And please note what is the size of this nanoparticle which we simulated. It's like about 20 nanometers, so small enough and so good for microelectronics. We're not going to discuss all the things where these topological configurations and the related structure can be used, but what we're going to discuss in detail is the negative capacitance. This is time remaining, okay, 2 minutes, okay, the time is running fast. Okay, so I'm trying to run fast quickly about this. So why these Hopf-ions are interesting? Because they can show that in ferroelectric nanoparticle, negative capacitance can exist. Okay, let's skip this since I don't have time and go to the technological issues. Basically, why are we interested in this like negative capacitance? Okay, for two reasons. We now microelectronics reached the limit where the consumed power does not allow this microelectronics to be efficient anymore and to pack more, let's say, field effect transistors into the microchip. If we can decrease the consumed power, then we can make the new kind of the chips, and this will be the revolution in the microelectronics. Now, we know pretty well from the school course that negative capacitance cannot exist. This is like the law of energy conservation. And nevertheless, we have shown that it can very well exist. And if we take the small nanoparticle, let's go to it. If we take small nanoparticle about the size of like 20 nanometers, we can find out that this nanoparticle is split in exactly 2 domains. And if we make this nanoparticle in a disk shape, then it means that if we apply the charge to the plate, then in order to compensate this charge, this domain wall should move. And since it moves, its length becomes smaller, and the area. It means that it decreases this surface energy. And then it means that actually it overshoots because it would love to move a little bit more than it's obliged due to electrostatic effects. And if it moves a little bit more, then the electric field which appears there overcompensates the electric field due to applied charges, and it means that we have negative capacitance in our nanoparticle. As simple as that. Now, the time is over, right? I believe.
No, I misunderstood the hand signal.
Huh?
I misunderstood some hand signals, so you still have some time.
How much?
15 minutes.
Oh, 15 minutes. Good.
Yeah, I misunderstood.
Okay, then let's come back. If I have 15 minutes, it's like a slightly different story. Okay, so what can we make out of this negative capacitance I was talking about? Okay, first thing, of course, the conservation of energy is the thing which we cannot violate, and the thing about this negative capacitance in itself, in a one capacitor cannot exist. Okay, it can be created, but it's not going to be stable. So what we have to do, if we want to make this field effect transistor, basically what you see on this picture is the field effect transistor. We have, then we have a combination of 2 of them. Let's say this negative capacitance, this one with the ferroelectric, divided in 2 domains, and then another one. Together, the full capacitance is positive, but it can be as small as, okay, very small, the total capacitance close to 0, and it means that actually electric fields and voltage by which this field effect transistor operates can be done about 100 or even 1,000 times smaller than what we have now. It means just reduced, heat, and it means that new kind of microelectronics, which can be like at least 100 times more efficient, can be constructed. Now, this is just like, the device which we propose. So this is just capacitor with the ferroelectric inside, 20 nanometers in diameter, divided into 2 domains. Now, is it good enough? Not quite, because we can analyze it work a little bit and find out that basically once we've done it, its parameters are completely fixed, and it's not like, because all the sizes are predefined, we cannot vary much its characteristics of this transistor. But what we can immediately do, we can make immediately a little bit more complicated device. We can code this ferroelectric with the usual dielectric one, then the effective circuit is like that. And well, it's a little bit boring analysis, but it's on like, I don't know, first year student available, that if we actually change the size of this, our dielectric coating, we can change the characteristics of our field effect transistor as much as we wish. We can achieve, all these possible best characteristics. Let me find where it is. Actually it's here. So depending on the size of this coating, we can be in different regions, and there are 2 critical sizes of this coating for this ferroelectric size of 20 nanometers. And if the coating is between these 2 critical sizes, then the capacitance of this gate on the, of this field effect transistor is negative, and then its characteristic can vary with the size as much as we wish. Now, those are these characteristics, which is dependence of this drain current, which goes through this let's see. So drain current, this is field effect transistor, the usual construction. So one plate, another metallic plate, this is capacitor, this is dielectric, which protect our semiconductor where we have this source and drain parts, which protects it, from leaking electricity from this capacitor. And we can find this IV curves, so to say, and then we can choose changing the size of our dielectric coating. We can find the best characteristics of our field effect transistor, and so that on one hand, its characteristics are good enough, and on the other hand, it's stable, meaning its performance is stable. So then, for every given material, we can find the optimal size of the coating, which provides the best performance of the field effect transistor. So this is what we are going to do. And then there is one more beautiful effect, which comes from the negative capacitance and this construction of the ferroelectric, mainly. If we find out what is the frequency of oscillations of this domain wall, and especially when we have this negative capacitance, we find out that it's sub-terahertz or terahertz region, which is quite convenient for application because, you can find any release or any review and find that basically what our modern technology is going to die without are these beautiful and small terahertz sources and terahertz devices. Because our usual terahertz devices have the size, I don't want it to be much too critical, but they're not small. And this what makes, their technological use for the moment impossible. One of the best technological use for, and with this, the size of this terahertz source, for example, can be scaled down to just 20 or 30 nanometers. So it's really microelectronics capable to work in a terahertz or sub-terahertz spectral band. And well, those are just characteristics of how we can calculate them, the characteristic of this, our thing. And basically this terahertz or sub-terahertz radiation has been found experimentally. We described how many years now? About 4 years ago. What happens if we have this ferroelectric films split into domains and what kind of frequency behavior we can expect. And last year, the paper in Nature was published when they have seen exactly what we have predicted before, for that. Well, and this just, to finish the story, those are, this is possible technological use for our terahertz devices. Well, I missed probably the most interesting and the most important one here. This is for medical diagnostics. Since terahertz irradiation is not as damaging as X-rays, on the other hand. And on the other hand, is very penetrating. Because of the wavelengths into the biological, media. This is absolutely irreplaceable tool for the medical diagnostics. It can, for the early diagnostics of the things from heart diseases, cancer, any damage of the, biological tissues. And, so the demand is going to be extremely, high. And another thing which I didn't put here is pharmaceutic. Again, because it's not X-rays, it's not damaging these organic molecules. So again, it's not my invention. I was reading this in one of the press releases that that it's going to be irreplaceable for pharmaceutic and composing new kind of medicine and control the composition and organization of the biological molecules which are the part of the medicine. And actually this is the end of the story. Maybe one more thing to tell, because China was somehow mentioned in one of these introductory talks. And I remember I was reading one of the press releases. They didn't say exactly, well, it was said that it's negative capacitance, which is interesting. And this press release was saying that Chinese government waived all the taxes from all the companies and all the scientific institutions which investigate negative capacitance. So it means that they understand pretty well how important for the electronics this negative capacitance may be. Okay, so we came to the end. So this is conclusions. So basically this negative capacitance is a domain-provided effect. And it's again very interesting because it was Rolf Landauer who first indicated that negative capacitance is possible. Then it was a lot of publications and a lot of patents in which this negative capacitance was used, and it gave me like a beautiful feeling reading these patents. Because, well, imagine that you are reading the patent about what? Some robot doing the homework and cleaning your house. You read the patent, you see the technical drawing, and you see one black box there, which says time machine. The part of this robot is time machine. Of course, you understand immediately that this kind of robot can be extremely, extremely efficient with a time machine. The only small detail, not of one of, okay, and then imagine that this patent doesn't tell how to make this time machine. So there are a lot of patents about all this like possible microchips which says, okay, and this is negative capacitance. You will never find how to make this negative capacitance. Now, all of us, we know how to make it. And, well, so our finding says that it's exactly two-domain ferroelectric which provides this negative capacitance, which immediately gives the characteristic size for all these industry-used ferroelectrics between 5 and 20 nanometers, and then negative capacitance-based resonators open actually new route and new area for this, okay, new kind of technological devices. Well, not the advantage that they're small. They consume about 100 or 1,000 times less power than the usual one, because basically what is happening there, instead of usual LC circuit, for which we may have the resonance, we have negative capacitance, positive capacitance line, and it means that the power which is consumed there is like 1,000 times less because it's not the inductance there. Okay, then I think I'm done. Thank you for your attention.
Thank you, Valerii, for a very interesting talk. And we have about 4 or 5 minutes for questions. Yes?
You said that in ferroelectric substances, you could have negative capacitance and you can make a generator of terahertz frequencies based on this resonance. My question is, what determines the frequency of this resonance? Frequency of the cells, what determines the frequency? Can you tune this frequency, and what is the line width of the resonance?
Okay. The frequency is like, okay, comes from the, from the frequency of the oscillations of the domain wall. Just, if you take just the usual ferroelectric, which is like PTO or something like that, you will immediately find that if you have this, multi-domain structure, it will be in a terahertz region. You can tune it, you cannot tune it 10 times, but you can tune it a little bit, changing just the sizes of your ferroelectric nanoparticle in which it is there, and changing a little bit, changing the number of the layers there.
And what is the line width? You see, the problem with terahertz generators is that usually the terahertz generators are pulsed and they generate continuum. So it's not a monochromatic terahertz frequency. And that's a main problem. I mean, people suggest to use antiferromagnets, but antiferromagnets, they also have pretty wide band. And my question is whether you can overcome that in this case and create really monochromatic terahertz frequency generator.
Okay, excellent question, thank you. Basically, we're doing, calculations and simulations. The preliminary answer is yes. That's why, that's why it is so interesting, because it doesn't work the same way as like, antiferromagnetic resonance, because this motion of this domain wall, in a sense, is very well controlled. I mean, not by us, self-controlled by the ferroelectric construction.
Thank you.
But thanks for this question, and that's why we really look at it as the very perspective direction.
So do we have another question? So maybe I'll follow up on that, because I was also curious about this terahertz generation. I don't quite, so just by putting a field on this weird new capacitor that, I don't know if anyone's built it yet, you will generate terahertz, and it can also be used as a detector. So it has some things in common with Josephson junctions then.
No, it's not the Josephson junction.
No, but I mean the fact that it can be used as a detector and a generator of the radiation, of terahertz radiation. Right?
Didn't quite get, Laura.
Oh, because the Josephson junction can generate microwaves as well as detect microwaves. And so my comparison is that this device, if we could build it, would be used both for generating terahertz and for detecting terahertz. Is that correct?
Yeah, absolutely. Yes, so we can make, both of them. That's why one of the applications is, use it for the next generation of our iPhones when we make them, or for space communications where terahertz is preferable, or for example for filtering. This is exactly, to filter, this was the question of how we can make this monochromatic one. Just the use, terahertz source, and then terahertz filtering, which make, really,
so what would be the main roadblocks in building something like that?
Well, it's it's another question, and since we are not only physics but technology as well, basically what we are looking at, and let's put it that way. Now, as many of you know, I am not working for Argonne National Laboratory anymore. I am working for the company. And this is exactly what we're looking for. We're looking for another company or foundry which will be producing these ferroelectrics for us and for other technology. And as many of you know, with the foundry, the negotiations are very simple and straightforward. If we are going to order a chip which will have 10,000 this field effect transistors with the ferroelectric, they are going to do it like that for tomorrow. When they tell them, please make one, they say,
Okay. So before we thank you again, what I'd like to do is present you with this certificate. Thanking you from the conference.
Thank you so much. Thank you, Laura.
Thank you.